You have fallen into Event Horizon with John Michael Godier. For today's discussion on possible organics found on Mars, John is joined by Dr. Kevin Hand, a planetary scientist and astrobiologist at JPL, who works on numerical modeling and laboratory investigations concerning the physics and chemistry of icy moons and ocean worlds in the outer solar system. He was a scientist aboard James Cameron's 2012 dive to the bottom of the Mariana Trench, and he was part of a 2003 expedition to hydrothermal vents in the Atlantic and Pacific Oceans. He has made 9 dives to the bottom of the ocean.
Dr. Kevin Hand, welcome back to the program.
Thanks, John. Pleasure to be back.
Doctor, I have to celebrate something to begin this off with, and that is the Perseverance Rover, which is a resounding success. And it also seems like everybody that chose where to put this, Jezero Crater, really nailed it correctly, because talk about interesting. And I look at the formation, the overall formation involved here, which is the Bright Angel Formation. It still looks like a riverbed.
That's right.
It still looks like it. It's like you look at that formation and it's like, that is a dry riverbed that has fossilized. And even after however many billions of years, I mean, this is a long time ago, that still is recognizable. And I actually really enjoy that, because we're missing a whole lot of Earth's history from that period. It didn't preserve. It subducts or it weathers and it's gone, other than a few hints here and there and things like that.
Right.
Mars still has it, though. And we can go there and probably learn a lot about Earth just simply from that, because we're missing that period in our geologic history, whereas it's not. Now, interestingly enough, you have made probably one of the greatest discoveries in my astrobiology interest lifetime, which is about 40 years now, above perhaps the labeled release experiment, which was inconclusive, and the Allen Hills 84001, which was inconclusive. This one's going to be a lot harder to knock out. Lay out what you found, especially the chemistry, with the Shayeva Falls find.
I want to just start, though, by emphasizing something that you really grasped onto there, John, which is the context of this discovery. Neretna Vallis is the valley that cuts through the Jezero Crater rim. And 3.5 billion years ago, we don't know the exact timing, but let's say it's about 3.5 billion years ago, that river valley was flowing with water and fed into Jezero Crater and filled up Jezero Crater and gave rise to the delta deposits in Jezero Crater that over the past several years, the Perseverance rover has made its way up and through, and then eventually out through Neretna Vallis itself. And so, just like a fossil hunter here on Earth, say traveling in Utah or Nevada or where have you, you would walk up a dry river valley, looking at the cliffs on the side and looking at the rocks and sediments below your feet for signs of past life on Earth. Now, on Earth in Utah and Nevada, a lot of that sort of fossil hunting is dinosaur bone hunting and looking for these large macroscopic creatures. But of course, the dinosaurs, they date back to 65 million years ago and lived for a couple hundred million years. On Earth and potentially on Mars, if you go all the way back to 3.5 billion years ago, on Earth, all that existed were microbes. And as you mentioned also, not many 3.5 billion year old rocks are left over here on Earth. But on Mars, we've got lots of rocks from that time period. And so with Perseverance, we were able, like a fossil hunter, just to noodle our way up this valley. And sure enough, we found these deposits where, as we'll get into, we've identified some potential biosignatures. And who knows, maybe what we're seeing are in fact relics of ancient microbial life fossilized in the sediments of this ancient river valley.
And it looks like the place to go. It's clearly a sedimentary valley, and this is where you need to be.
100%.
What's interesting to me about that environment is that it took a while to dry out. It had water, and then water just slowly went away as it did everywhere on Mars, and except maybe underground. But the bottom line is that if you were going to go and try and find any kind of evidence of microbial life, which is a whole lot harder than a dinosaur, as you say, microscopic,
Yeah.
but you do have ways to look at that mineralogically and chemically. Now, what were you looking for when you were intensely studying this rock and taking a bore sample out of it?
Yeah, so we weren't actually looking for what we found. I mean, we were in a way certainly, but broadly speaking, we're always looking for signs of organic compounds, and we can get into exactly what we found at Chiava Falls with respect to organics. And then mineralogically, we're always on the lookout for reduction and oxidation gradients. What do I mean by that? Well, geochemistry and biochemistry really is the economy of electron transfer. And reductants, reduced minerals or compounds, have a lot of electrons to give away. Oxidized compounds are always looking to accept electrons. You can think of these as like the terminals on a battery. If I give you a flashlight and some AAA batteries, those AAA batteries will eventually equilibrate because electrons will migrate from one terminal to the other and the batteries will eventually die over the course of years. That's sort of an analogy for a standard geochemical reaction. But now if you take those batteries and put them in the flashlight and turn the flashlight on and complete the circuit, now you're accelerating the flow of electrons between the terminals and you're discharging the chemical energy stored in the battery. And that's essentially what biology does, at least here on Earth. We accelerate the geochemical equilibration of reduced compounds with oxidized compounds and the transfer of electrons between the two. So in the retinovalis, and on Mars more broadly, we're always looking for minerals that are out of equilibrium. And for the most part, everywhere we look on Mars, we find rusted, oxidized rocks, predominantly iron rocks. But these leopard spots, these little features that we ended up finding, revealed to us reduced iron phases, reduced iron sulfide, reduced forms of iron mixed with phosphate. And so the identification of these reduced minerals in these little zones, which we can get into kind of the geography and the importance of that in a minute. But we found these reduced minerals in these zones, and then we found organics in the matrix material outside of these zones or these leopard spots. So that's kind of the overview, and then we can dive into more detail on some specifics there. But does that make sense so far?
Absolutely. Continue.
So I want to kind of differentiate at a high level potential biosignatures. Of course, as we know, life on Earth depends on liquid water and is built primarily of carbon. And when we think about kind of our roster of potential biosignatures or measurements that might be an indication of past or present life, we've got a pretty interesting, extensive roster. And perhaps primary amongst that roster is the context. And we already went through that. This is a dried riverbed. And so the context makes sense. So we can kind of check the box there. Next up is carbon and organic compounds. Some would argue that just even the detection of organics on another world like Mars qualifies as a potential biosignature. And I tend to fall into that column. I tend to think that the identification, the detection of organics anywhere serves as a potential biosignature. But actually being confident about something relating to past life, you don't want to depend on just one potential biosignature. You want to have a few of them checked off. So At Neretnevalis, we found organics and a very good signal of organics. And the type of organics that we found are ringed carbon compounds. This is somewhat similar to what you would find in Archean or really old rocks here on Earth. So that was very exciting, just that detection of organics. Then there's a whole suite of inorganic potential biosignatures. And here's where things get particularly interesting. Just as one example of an inorganic biosignature or potential biosignature, a dinosaur bone would be an inorganic potential biosignature. It's a type of rock, skeletons, bones are a type of rock made by an organism. And so that's, dinosaur bones, great. You could check the box on an inorganic biosignature. Another example I like to give, I'm sitting in a building here at JPL. At a civilization scale, the buildings that we humans make, those in some capacity are certainly an inorganic potential biosignature. So there's a whole different kind of array of inorganic potential biosignatures. Some are structural, like skeletons or buildings. Others are more sort of geochemical, and that's what we found at Neretnevalis. And that comes back to this redox kind of gradient, this zonation of minerals that indicate that life could have helped mediate the geochemical reaction between reduced phases and oxidized phases in the sediments and in the water surrounding the material. And that kind of inorganic biosignature is almost like finding a dead battery in the environment. And that perhaps could be what we found with these leopard spots, sort of a microbial version of a dead battery.
Now, when you look at the structure of the leopard spots, you can see the ring around it that you were mentioning. And now that's, and please correct me if I'm wrong here, that's called a reaction front, right? If that were something that we found here.
That's right.
So it even looks structurally like that.
That's right. And so that reaction front, the leopard spots, the interior, we've got this iron-rich material, that Vivianite, some of that Greigite, these reduced iron phases associated with phosphate and sulfur, respectively. And then, as you mentioned, there's kind of this ring of the reaction front around. And this is an imperfect example, but continuing to sort of use the battery analogy. Imagine if you could continue, or it's almost like a garbage pile in a way that it can keep on expanding as you eat more and more food and produce more and more waste. Microbes do that and work together. Sometimes you've got sulfate reducing microbes working with iron reducing or even iron oxidizing. All sorts of different microbes work in symbioses to kind of help each other out when it comes to eating whatever is available around them. And so with these leopard spots, if they are in fact biogenic, i.e. produced by ancient life on Mars, you would have had microbes surrounding that reaction front and mediating the consumption of, say, sulfate in the water and organics in the water, and in their metabolic processing, producing or eating the reduced phases. Somewhat analogous to us eating whatever is around us and then concentrating it into a garbage pile.
So effectively, over the course of NASA's exploration of Mars, we've realized that Mars is a microbe food factory. It has everything a microbe needs to eat, basically. But is there anything you can think of that we haven't seen that it might also need? Presuming it's very similar in function to Earth microbial life.
Yeah, it's a good question, John. And the short answer I would say is no. By just about all accounts, we can check the box on the habitability of Mars. Perhaps not globally, similar to different ecosystems on Earth. Some places are better for life than others. Perhaps Mars had a similar situation, but for Jezero, we've got indications of past liquid water. We've got plenty of availability of the key elements. I mean, even the fact that we're seeing phosphorus here, that is particularly exciting because on Earth, sometimes you find environments where maybe you've got water and some of the other compounds you need, but you're limited by the phosphorus abundance. Phosphorus is key to our DNA, RNA, and our ATP, our adenosine triphosphate. So in this particular case, we've got these phosphate-rich leopard spots. And so not only do we think that this region could have been habitable, but it's also, there's a really strong case for the phosphorus availability.
Now, in the same sample, you also had not only leopard spots, but also poppy seeds. Now, are those just smaller versions of the leopard spots? How do they play in here?
Yeah, we don't really know. And hopefully we'll get the chance to go back and study this region in more detail. But it may be that the leopard spots are just a more kind of mature version of the poppy seeds. Maybe the poppy seeds were kind of just getting started in the sort of zonation process. And here, John, it's important that let me describe a little bit of like how you might get this done abiotically. And here again, part of why we want to go back is to take a more detailed look at the geochemical and geophysical environment of Neret Nivalis and Chiava Falls to see whether or not we've been as parsimonious as possible and examined all possible abiotic mechanisms. Typically, it can be kind of hard, especially in an environment. So this river, and we even think that Neret Nivalis, right around Chiava, there was kind of a localized small lake. So you would have had a river flowing and then a kind of small ponding area that made this small lake, and then an outlet channel that continued to feed down into Jezero Crater itself. And that river and the lake would have had quite a bit of sulfate in it. Sulfate is a salt that we find in all sorts of different lakes and river environments. There's not actually that much sulfate in our ocean. The dominant salt in our ocean, of course, is sodium chloride. And a fair bit of the sulfate actually comes from continental weathering, but that's a whole different story. But if you go to a place like the Mojave Desert or Mono Lake or up around Salt Lake up in Utah, sulfate or SO4, the sulfate ion is pretty common in waters. And on Mars, we would have had quite a bit of that in no small part because the volcanoes were constantly spewing out sulfur compounds and sulfur dioxide. And so you would have had a dissolved form of that in the liquid water environments of the rivers and the lakes. So you got all this sulfate, and then microbes, if they do have a good electron redox pathway, as I kind of walked through before, they can take that sulfate and make a meal out of it, as long as they can do electron transfer to get the sulfate, which is an oxidized form, into sulfide, which is a reduced form of sulfur. Abiotically, doing that reduction process is a little bit tricky, but if you get up to high temperatures, it can be done. And you might ask, well, how can you do that, say, in a river valley on Mars? Well, one of our hypotheses for the abiotic formation of these leopard spots is that maybe some of these sulfate-rich sediments with iron in them and some phosphorus had a hot lava flow over them, or some high temperature hydrothermal activity, some sort of geophysical event that then raised the temperature of the sediments sufficiently that you could drive the formation of these leopard spots and poppy seeds. I think that's entirely possible, very plausible, and who knows, Mars is an entirely different planet, and things could happen a bit differently on Mars. So, I definitely think it's important to hold that abiotic hypothesis up as perhaps the more conservative hypothesis. The biogenic hypothesis is more extraordinary. And of course, the more extraordinary the hypothesis and the claim, the more extraordinary the evidence needs to be. And so while I think the abiotic hypothesis is certainly viable, it requires, in my opinion, a little bit of special pleading to get these leopard spots and poppy seed formations. And I find myself sort of scratching my head and like, okay, if we just had a blanket heating mechanism, maybe you wouldn't expect to find these kind of smaller zonation regions that we see as leopard spots. Microbes love to do that. Geochemistry is a little less prone to doing that. So the sort of shape and the way these things have formed at Chiava Falls, I do find pretty compelling from a biogenic hypothesis. But we got to be careful, we got to be cautious, and we just got to get these samples back.
Absolutely. Now, is it possible to tell in situ anything about the surrounding rock that might reveal if it was heated to relatively high temperatures, my sense of this, to get that chemistry going abiotically? I mean, we all know that Mars was volcanic, but this isn't really that area of Mars so much, at least as far as we can see. So the question is where does the heat come from? And would that leave a mark on the surrounding matrix?
Yeah, and John, one of the things that we've been looking for and tracking on Mars, and in fact, where we are now, kind of on the outside of the crater, we've been doing a lot of this. You certainly could have intrusive features. So think of like a dike coming up through the crust, kind of sending a plume or a fracture of hot material up to near the surface. And to the west of us, there's lots of volcanic activity. You can come up with a whole bunch of different scenarios to try and arrive at a hot kind of contact margin that could get the job done. But as of yet, we don't have any smoking gun for that. We have nothing we can point to say, that's the abiotic explanation for these features that we're seeing.
A nuts and bolts question about perseverance. All right, so the sample that you're looking at closely is Sapphire Canyon, which was taken out of Chiava Falls, the rock.
Mm-hmm.
Now, how does Perseverance do that? And how do you what is your resolution limit on what you can tell versus what you could tell if you had a sample return?
Yeah, so once we get these samples back to Earth, which is something that all of us on the science team are eager to do, especially with samples like the Sapphire Canyon rock core that we collected at Chiava Falls. Think of when NASA decides that it's going to move forward with a rover like Perseverance, a call goes out to the community, an announcement of opportunity that basically says, listen, we've got this many kilograms and this much power and this much data uplink and downlink that we can dedicate to a suite of instruments that will be bolted onto the robotic arm and onto the rover itself and sent off to Mars. And typically, from a mass standpoint, those allocations are in the range of a few to maybe a few tens of kilograms. And so the instruments that we have been deploying to analyze Chiava Falls in situ, instruments like the SHERLOC instrument, of which I'm the PI, and Pixel instrument, which did a lot of the mineralogical analyses. These are instruments that weigh in the range, if you include everything, 10 kilograms. And that's what's giving us all these detailed analyses. You get these samples back to Earth, and now we can deploy instruments that are the size of a building to analyze at the nanometer scale. Right now, we're able to analyze at sort of the tens of micron scale, and we're only able to do a very specific set of measurements. We get these back to Earth. Spatially, we can look in 3 dimensions at the core without even harming it. We can use ultra high resolution CT scans before we even open up the tube. Once we open up the tube, then we've got scanning electron microscopy, transmission electron microscopy, all these different acronyms of ZANES, and sending high energy particles through the sample to really characterize every element, every compound position, every functional group and band, and linkage between elements. And so, as good as Perseverance is, it has a pretty humble and modest payload. It's incredible that we're able to do what we're doing, but goodness knows we get those samples back to Earth and we'll be able to dive into these samples in much greater detail and look for things like, maybe there are tiny little mineralogical skeletons of any microbes that may have once existed. That would be one of the first things that I'd be excited to look for, to figure out if we're dealing with abiotic minerals or biogenically mediated materials. On Earth, we can look for tiny little microfossils or inorganic minerals that are most commonly generated by microbes. And we can better characterize the organics, and we can figure out if those organics had any relationship to ancient microbial membranes, or if the organics are just kind of the standard inventory of organics that we see in asteroids and interstellar media.
So I have an off-the-wall question. Now, we're looking at basically a pond that, river reducing pond, those puddles form. Now, since we don't understand the process of abiogenesis yet, we have a few ideas here and there, but we don't understand the process. Is it possible that you're seeing protolife? In other words, is this just too far along and points to microbial life, or could it instead point to its precursors?
So I'll give you an answer that I tell my students to use more often than they're generally inclined to. And that's, I don't know. I love thinking about this stuff, and you're absolutely right that we don't know how easy or hard the origin of life is. And certainly one of the exciting prospects about searching for life on Mars is to potentially find a second tree of life, to find a second origin of life. I think perhaps as we talked last time, I described that kind of difference between, say, life on Mars and life on Europa, where life on Mars could have been seeded by life on Earth, or life on Earth could have been seeded by life on Mars. And so it's it could be a little tricky, even if we find evidence of life on Mars, to know distinctly that it represents a second independent origin from life on Earth. Because we're not going to find DNA or RNA in these 3.5 billion year old rocks. Those large information biomolecules do not last long in the geologic record. And that's really what we would need to differentiate the tree of life on Earth from the tree of life on Mars. So, back to your question, sure, we could be seeing sort of a proto-life, but as of right now, I have no particularly good way of constraining that question to a truly testable hypothesis. Maybe when we get those samples back to Earth, we can do more to investigate that. But this also, John, you kind of cracked open the Pandora's box of a semantic issue that my colleagues and I end up debating with words like prebiotic chemistry or biogenesis, et cetera. And that is that the moment you use a term like prebiotic chemistry, you are kind of anthropomorphizing and giving intentionality to that chemistry. Does that make sense?
Oh, yes, absolutely. It does. But what gives me the chills here is just the idea that because of the preservation we were talking about on Mars very, very early on, it would definitely give me chills if we found and cracked abiogenesis based on chemical evidence from Mars. And that then we have an even bigger question.
Right.
Yeah. Are we from Mars? Things like that.
Right. But the trick there and the challenge is that if we got these samples back and found all sorts of interesting things that we would classically label as prebiotic, we would not know whether or not later in Mars those compounds and that chemistry actually led to the origin of life. So if it turns out that the prebiotic chemistry does not actually lead to life, then is it truly prebiotic chemistry?
Well, it's a good question. There could be dead ends,
Right.
and there could be all kinds of things. We don't know. We're just
Right.
missing so much.
But then by definition, the dead ends indicate that it's not prebiotic chemistry in some ways. So it's a bit of a
That's
semantic
true.
catch-22.
Well, at the same time, though, that's a null result, which is just as useful as a positive. It tells you what it isn't doing, which is just as important.
But then it's just chemistry. It's not prebiotic.
True, but it is chemistry we didn't know about, and now we know to look for that.
Yeah.
Now, I want to ask specifically, and get back to the mineralogy. I want to ask specifically about Vivianite, and Vivianite was the thing that gave me a little bit of a. That's what pushed me over, because that is usually here. If we found it here, we would associate it with life, probably, unless it was in some geologic context that we don't. It isn't life. But for the most part, we see that in fossils where something decomposed. We see that in decomposition here on Earth, that chemical shows up with life. Now, in this, given that the structures also look like life, would you say that, and this is going a little bit further than conservative, but would you say that life might actually be the simplest answer for this by Occam's razor?
I don't know enough yet. I think there's definitely a. I think there's a strong case that Occam's razor points in that direction, but many of us have been poring over the additional data that we have for this region in the Retina Vallis, and there will be more manuscripts that you'll see on other rocks that we examined in this valley and other features that we saw in this valley. I'm hoping that this work will catalyze more work in labs and in environments here on Earth to better understand the linkage between Vivianite and abiotic and biogenic pathways. Because you're absolutely right in that there is quite a bit of interesting work that's already been done that helps kind of bolster the case towards this potentially being biogenic. But the way science works, I think the next step is for us to do our homework here on Earth and look at the kind of boundary conditions for biology on Earth and where Vivianite and Santa Barbarite and all these different iron phosphate minerals, where and how they form, and whether we can kind of propagate that formation into a Martian analog environment. So we've got the spacecraft measurements. Now we'll do a bunch of work in the lab to see whether or not our hypothesis can be tested in the lab. And in the meantime, we'll continue to explore the region around Jezero Crater with perseverance. And at some point, hopefully we'll kind of turn around and come back and make another pass through the Retina Vallis and get a chance to collect another sample and do some more detailed analysis of other regions in the valley. So, that was a roundabout way to kind of avoid a direct answer of, do I think Occam's razor points to these being biogenic? But I think you can appreciate my desire to be as cautious as possible with the biogenic interpretation.
Oh, of course. But remember, I'm not a scientist. I'm a science fiction author, so I can push things just a little bit further and
That's
see
right.
what we get.
You were free to speculate, and I love that you guys are excited about this. We're obviously passionate about it, and
that's what I want to see the most in life, is the discovery of microbial life in the solar system, a second abiogenesis in the solar system. I have absolutely no idea if we would ever see intelligent alien life or anything like that. I'm leaving that off the table because I probably only have 40 years left. But I'll bet you we can crack abiogenesis in the lab, or we can go and find a microbe or a fossil of one.
Right.
And if we don't find it, that answers my question too. So So that's what I'm hoping for. Now, next mineral. How does hematite play into this? Now, Mars is basically a hematite planet.
Right.
You know, you remember the blueberries from another rover. That one of the first things they saw were these hematite. And you don't need biology for hematite, but it can play into biology, right? Because it's it's iron in the same way. So how does it play into the leopard spots?
I'm definitely not the best person for that kind of bridge with hematite. They're mineralogists, geochemists that are much more knowledgeable on that. And so take the following with a little bit of a grain of salt. So elsewhere in Jezero, we have seen some concretions. Do you know what concretions are? Have you ever kind of seen
Oh,
these
sure. There's
out?
one sitting on a nice looking one sitting on the shelf next to me.
Right.
I like them. They can be really interesting and really puzzling because they can mimic fossils, and just weird.
That's right. And we saw some hematite and some concretions further down in Jezero. And we didn't have kind of the same opportunity to study those in detail. We had to kind of keep on moving. But as far as the direct connection to these leopard spots and hematite, I don't think we've made a clear connection yet. But you're right in that elsewhere on Mars, hematite has been pretty exciting in the kind of variations on iron chemistry that we've seen.
And water, for that matter.
Hmm.
It also gives you clues about that. But I think at this point, sitting in with Perseverance, sitting in what's at least to me clearly a riverbed,
Hmm.
I think we know the water was
Yeah.
there. Now, the next question, though, is about that. What about the rocks around Shayeva Falls? In other words, I see this extensive geologic formation there. And my question is do any of those look interesting in this regard to look for more leopard spots or anything like that? Or did you just go for the very best sample that you could see given the time you had to look at the other rocks?
Definitely not the latter. We kind of, in some ways, stumbled upon these leopard spots and very compelling rocks. So in the manuscript, there's that figure of looking down on the valley. And we knew that Bright Angel was intriguing just visually. We could see that it was bright and kind of different from the surrounding. And we did look at an area called Walhalla Glades and another spot called Grapevine Canyon. But then Chiava Falls, which is right up kind of near the edge of the river valley and is in close contact with the margin unit, which comes back to my earlier mention of lava flows. It may have been that the margin unit itself represents a flow of hot material over what at the time was Chiava Falls, helping mediate the abiotic reduction of the sulfate and the iron. But I would have loved to have spent much more time going around Bright Angel, more time over at the area on the other side, on the south side of the riverbed, called Masonic Temple, where there's Mount Spoonhead, and then we also had kind of scoped out further upstream, so kind of to the left in that image, looking at some deposits that might have been similar to Bright Angel and might have also had things like leopard spots or poppy seeds. And so we didn't kind of survey around in much detail. We went in there, we saw some interesting things and made these discoveries, but then we had to keep moving. And we certainly would have loved to have spent more time if we were able to.
Are there no-go areas where the engineers are like, no, you can't take that rover there, even though they look absolutely fantastic from a geology point of view?
Yeah, there are slope constraints, in other words, angles that are too high. I think these days it might be something like a slope of 26 degrees. If you get above that, then you can't get onto that slope, or it requires special approval to go on a slope above that angle. Might be lower, it might be 22, I forget. So the angle of the slope, not surprisingly, the abundance of nefarious rocks that can confound our roving. Also, dunes, or as we call them, bed forms, the small ripples In that image of Narette Nivalis, you can see what look like dunes, but dunes are generally considered to be kind of a larger version of these bed forms. These tinier ones are kind of the scale of the rover. Perseverance could probably make it over many of these, but it's just better to avoid them than risk getting stuck.
Yeah, well, I mean, they have gotten stuck in with past rovers. I believe Spirit did. Things happen. It's Mars.
Yeah.
You're just not.
Years ago, actually, I was on a wheelwear Tiger team for Curiosity. As you guys may remember, the Curiosity rover had problems with its wheels where the ventifacted rocks, the very sharp rocks on Mars in Gale Crater, punctured all sorts of holes in the wheels. And to this day, Curiosity's wheels are still
chewed up.
You look at them and it's Curiosity's kind of roving down the highway with a flat tire or two. It's still going well, but nevertheless, when that wheel wear first started to happen on Curiosity, a bunch of us took the Scarecrow rover out to Dumont Dunes here in California. The Scarecrow rover is a mass model for mobility. What do I mean by that? Well, on Mars has got 1/3 of the gravity of the Earth, and the mass of Perseverance, or in this case, Curiosity, then puts a certain amount of force on the wheels. And the mass model Scarecrow essentially adjusts the amount of mass that we've got on the chassis such that the wheels here on Earth experience the same amount of force that they would experience on Mars. So we took it out to Dumont Dunes and tried to get it stuck in the sand in the dunes. And we roved it over natural bed forms and small sand pockets and stuff. We even had shovels with us, and we made different things that were kind of Martian scale. And in just about all scenarios, the Scarecrow rover eventually roved its way out of the sand traps that we made for it. There were a few like large scale ones that it just kind of kept on churning and churning, but the smaller scale ones have made it through. So the rover planners, they don't want us driving over these bed forms, but in the worst case scenario, I'm actually pretty optimistic that Perseverance, and for that matter, Curiosity, would be able to get through some of these.
Now with the wheels, now I've certainly seen the chewed up wheels, and I was actually rather surprised to see it. I'm like, man, that's a harsh environment there.
Yeah.
But in comparison, did Perseverance use the same wheel design? And two, what's its wheels look like right now?
So the Perseverance wheels, it was an interesting challenge for the engineers. They were basically given the same mass allocation for the wheels, but they had to make the wheels stronger. And I forget exactly how they did that, but the wheels on Perseverance look somewhat similar to the wheels on Curiosity, but the metal's a little thicker, and the grousers, the sort of metal ribs that go across the wheels, are a little sturdier, and I think they're more frequent. But in the design of the Perseverance wheels, the engineering team factored in some of the weaknesses that were discovered on Curiosity. And right now, the wheels on Perseverance look great. I think we even have a few little rocks hitchhiking with us in the bay of the wheels.
Now, my last question is what's next for Perseverance? What's the next target to go and characterize?
Yeah, it's a good question. It's one that our team is tackling right now. We are on the sort of downward slope of the western side of the crater rim. So we're basically kind of starting to get off and away from the crater itself. And there's a region kind of to the southwest called Lac de Charme. And that's an area that a number of us are excited about because it's a region, at least from the images and the spectroscopy that we've got from orbit, it's a region that looks like it may have rocks that have been less affected by the geophysical and geochemical processing that occurred as a result of the Jezero Crater formation. And so, in other words, those rocks further to the west may give us kind of a more native Nowakian basement rock. In other words, access to some less altered, really, really old rocks on Mars. And from a geochronology standpoint, one of the things that we're doing on the mission is collecting these rocks that will allow us to then date them back here on Earth and put brackets around when different things formed on Mars.
All right, Doctor, thank you for joining us today. And I'll bet you there are many more discoveries left in Perseverance. I'll bet that we may not even be past the halfway point. It's already been fantastic. And I hope someday we'll check in again when the next discovery is made.
You're absolutely right. I think we got many discoveries to come, both on Mars and elsewhere in the solar system and beyond. And thanks to you and your listeners, we're excited to share this all with you. And with any hope and luck, we'll continue to be able to do this kind of exploration.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.